USDA logo, United States Department of Agriculture.
Computer. Okay. Hello, today is Tuesday, March 15, 2022, and I am interviewing Dr. Richard D. Mattis, Distinguished Professor of Nutrition Science and Director of the Ingestive Behavior Research Center at Purdue University. We are on Zoom today. I am Amy Morgan, an archivist in special collections at the National Agricultural Library. I have the honor of interviewing Dr. Mattis because he is the 2020 winner of the W.O. Atwater Lecture Award. The United States Department of Agriculture, Agricultural Research Service, established the award in 1968 to honor the memory of Wilbur Olin Atwater, considered the father of modern nutrition research and education, and to recognize scientists who have made unique contributions toward improving the diet and nutrition of people around the world. Welcome, Dr. Mattis. Please start by stating your full name and spelling it for us.
No, thank you very much. It's Richard Mattis, M-A-T-T-E-S.
Thank you. And now please share biographical information and begin as early in your life as you'd like.
I guess a good place to begin is I come from a family that's very much engaged in medical science. Father was a physician. One of my older brothers was a physician. My other older brother was an immunologist. So when I started college, the expectation was I would follow in the family footsteps and go on to a career in medicine. So I started undergraduate work at University of Michigan, and that was the plan, to be pre-med. But over the course of my undergraduate studies, I found myself drawn more to the field of public health. I saw value in focusing more on prevention than on treatment, having a bigger impact by working at the population level rather than at the individual level. I was interested in nutrition. At the time, nutrition was not really a prominent part of medical practice. And so over my undergraduate studies, I was a bit diverted. And so at the end, in 1975, I decided to go for a master's degree in public health, also at the University of Michigan and the School of Public Health there, focusing on nutrition science. I completed that work in 1978 and decided to go to Cornell University for my doctoral studies. And the plan was to study program evaluation. At the time, the Women, Infant, and Children feeding program was just beginning. I was intrigued by it. I thought it had tremendous potential and thought that in order to enhance the program, it was going to be necessary to build in strong evaluation components. And so that was the plan, to learn how to do program evaluation as my doctoral training. And I started out that way. In fact, I had my whole committee picked out. Everything was going along smoothly. But then I became friends with a psychology student at the university who said that he was in a course taught by a psychologist, but was also talking about nutrition and how the chemical senses, taste, smell, and chemical irritation, were really related to food choice and nutritional status. So he convinced me to go to a class with him. It was taught by Bruce Halpern, one of, in my opinion, the giants of the field. I was smitten right from the first fight. So it sounds corny, but it was my reality. I went to that first class and I thought, this is just important and exciting and novel and potentially impactful, and decided I was going to go that route. So I changed my committee. It was not a popular sort of thing to do at the time, but I changed my committee and started working with Shariki Kumanika, who was a new faculty member in nutrition science at Cornell at the time. And Bruce agreed to be on my committee, along with Frank Scheip, who was in food science. So they were really the heart of my doctoral committee. Shariki was interested in salt and hypertension. And so my dissertation sort of evolved into a study of salt taste in relation to risk for hypertension. And so my dissertation was looking at normotensive, prehypertensive, and hypertensive patients and evaluating their responsiveness to salt, sensitivity and scaling and preference and so on. And it was very much co-guided by Bruce and by Shariki. That ended up being the work that served as the science basis of my dissertation. And afterwards, I really was interested in a career that focused on this interface between nutrition science and the chemical senses. But I had come out with an unusual academic background. Part of me was still public health, where the philosophy is really, we have imperfect knowledge, but we've got a serious problem in front of us, and we have to do something about it. We have to act on existing knowledge and adjust if our decision-making is wrong in terms of how to remediate the problem. But I was also trained as a basic scientist in nutrition science, where the philosophy is much more study an issue until you understand it thoroughly before you make recommendations about how to change behavior or practice. So these were really antithetical avenues of training. But I think that they actually go together very well. I think what results is a pragmatic scientist, somebody that has deep training in a field, but takes on questions that are meaningful. Now, obviously, I don't for a minute mean to shortchange basic science, but it I think does create a professional that has a very real place in the community. So I left Cornell and took a postdoc at Sloan Kettering Cancer Center to work with Richard Rivlin to study bitter taste and thyroid disease. There were theories at the time that sensitivity to bitter compounds or lack thereof would lead to greater risk for exposure to toxic bitter compounds that were goitrogens, and so predisposed individuals to thyroid disease. And I spent a year there as a postdoc working on that issue, but it became clear to me as a new graduate that in a medical setting like Sloan Kettering, I didn't have a lot of colleagues that were interested in the chemical senses. And I really thought that was sort of my calling. And so after a year, I switched to a second postdoc at the Monell Chemical Senses Center. And Monell at that time was really the center of the universe for studying the chemical senses, the mechanisms and functions of the chemical senses. They were at the time, about 50 PhD scientists that were studying everything from reproductive behavior of prairie voles to how the chemical senses contribute to nutrition. And I spent 13 years at Monell, starting, as I say, as a postdoc and leaving as a full member and sort of head of their nutrition science program. And I left in 1995. I guess in 1994 it would have been then, I gave a talk on salt taste and hypertension. at a professional meeting, and Connie Weaver, who was the department head of nutrition science at Purdue, approached me after the talk and said, we have a position open. And we're interested in something that is an interface with nutrition science and food science, and what you're doing seems to sort of fit the bill. And we started talking, and I was intrigued by the opportunity to teach and work more with graduate students. And one thing led to another, and I transitioned over to Purdue. And I've been there since 1995, so almost 27 years. And for the first 20 of those years, I was traditional nutrition science, clinical researcher, teaching, doing research engagement, the standard sort of professor kind of position. But then in about 7 years ago, so around 2019, 2020, I was approached by the dean and asked to start a public health program at Purdue. There was a nascent program in the Department of Health and Kinesiology, but it was not thriving. And we had just formed a new college, and after strategic thinking and soul searching, decided that public health might actually be the glue that kind of held this new college together, and they needed a director. And there weren't many at the university that had a degree in public health, and not many that were as old as I was, and sort of in a position to step aside and take on a more administrative role. It was my first passion, and so decided I would give it a go. So I asked for a 5-year block of time to get the program up and running. They agreed, and after the 5 years, despite me, it actually did pretty well. And at that time, we had a new dean who thought that, again, this program had a lot of potential. And so the wheels were put in motion, and it became a full-on department in 2019. Being new and so on, it was not going to be easy to attract a bona fide scholar of public health to come and lead it. And so I agreed for a 2-year extension to get the department up and running, to get the faculty assembled, to get a mission and work out all the logistics and build the structure. And then to very consciously, purposefully step aside so that somebody with a real career in public health could take the reins. And so that's what happened. And I stepped down in June in 2021, and I'm actually on sabbatical at the moment, but we'll be going back to a split appointment. 80% nutrition science, 20% public health in August of 2022. So that sort of brings us up to date.
Well, thank you. It's very interesting. So now we're going to dive deeper into your research. You studied the relationship between salt, taste, and high blood pressure. What were the results of that research, and how can we benefit from those findings?
Right. So as I indicated, salt, taste, and hypertension were really where I started my career. We were interested in whether the taste of salt was a predictor for risk of hypertension, whether it predisposed people to consuming more salt, if they had a different sensitivity to or responsiveness to or preference for salt. And so we conducted quite a bit of research trying to determine whether there was a relationship of that nature that could be used for therapeutic purposes. I have to say, I think we learned a fair amount through all of that work, but it didn't turn out to be as simple and straightforward as we originally thought. That measuring taste could give us a clinical clue as to somebody's risk. But the work did result in a few observations that I think were impactful. One is during the course of that study, we tried to determine what all the different sources of sodium were in the diet. How much was added from the salt shaker at the table while cooking, how much was contributed by water, how much was inherent in food, how much was contributed by the food industry through processed foods, sort of trying to quantify the totality of sodium sources in the diet. We published that work. It was, in all honesty, not the largest and most comprehensive study, but it seemed to fill a void, and was really that work provided the basis of recommendations through the dietary guidelines for several decades. Again, it was a small study and didn't deserve that level of attention. But it just happened to be the right study at the right time and served that role. So I think there was some impact there. That work was done with a graduate student, Diana Donnelly, and that was published, I think, in 1991. We had also made observations that sodium intake was very high. That was no surprise to everybody. That was why everyone was concerned. But it was high across many cultures, and it had been high historically. There are accounts of the Chinese 3,000 years ago consuming diets with sodium levels very comparable to what we're consuming now. And all of this sort of suggests a biological basis for this behavior of consuming high levels of sodium in the diet. We don't know the mechanism. We don't know if there really is a biological basis for it now, but the observation is just too consistent to ignore. And I think it's one of the challenges that we face going forward to determine whether or not this is just something that is a sensory pleasant sensation, and that's what's driving it, or if there is something more fundamental. The difficulty in reducing sodium intake in the population would suggest it's not something ephemeral, that we are fighting some biology here. And so I hope our work sort of opened a window to that kind of inquiry, to see where that leads. And I think along those lines, we contributed, by no means initiated the work, about how exposure to sodium influence its acceptability and intake. So the work that really started this line of research was conducted by Mary Bertino and Gary Beecham at Monell, where they had shown that the level of sodium exposure in the diet was actually more important than the amount consumed. So you could have people consume high levels of sodium in capsules, so they never tasted it, but metabolically it was there, or you could reduce their exposure to sodium by limiting salt intake. And so you can manipulate intake and sensory properties independently. And what they showed was that it was that level of exposure, that frequency of exposure, that was more closely related to the preferred level of salt in the diet than was the actual metabolic challenge, the amount actually consumed. And we were fascinated by that. And our work, again, had been more directed towards hypertensive patients and pre-hypertensive patients. And so we conducted similar studies in that population and found very similar results. And that work, again, mostly done by Gary and Mary, is really the basis of the approach being used currently in public health practice. This idea of slowly ratcheting down salt levels in the diet in the hopes that people won't find food less acceptable from a sensory perspective, but will in fact learn, we call it a hedonic shift, adjust their preferred level of salt in the diet. So they actually prefer lower levels over time. And that's the approach that's being used in the public health practice presently. So that's, I think, sort of our contribution in that area. And there's clearly much more work to be done. Salt is still considered one of the big public health problems in the nation and globally.
Well, thank you. Please elaborate on your research into food form, appetite, and energy intake.
Right. So again, the basis was really a public health issue, overweight and obesity, and trying to understand what drives food choice and positive energy balance, eating more energy than is needed, resulting in weight gain. So one of our early, let me set the stage a little bit. In the 1950s, 60s, and up through the mid 70s, I think the research focus on food intake and overweight obesity was really centered on metabolism. The idea that rising or falling levels of protein, fat, carbohydrate, and how they were oxidized and detected were really the drivers of food choice and energy intake. But attempts to manipulate that were not particularly successful. And it led to a shift in thinking that started in the mid 70s or later 70s with the identification of gut peptides, particularly the first cholecystokinin. And that led to a kind of shift away from metabolism and more towards endocrine controls of feeding that persisted through the 80s, 90s, and early 2000s. But once again, we learned a lot of tremendous biology during that time. But the application to weight management was not straightforward, was not clear even after that time. And I think the field has shifted again, so that now there have been a couple of advances in science that allow us to answer questions that we couldn't answer before. We've developed techniques to understand the role of the microbiome in feeding and energy balance. And we've developed new technologies in imaging, particularly neural imaging, to study how the brain is responding to foods. And so there is a shift towards a focus on neural controls and brain reward mechanisms and sort of homeostatic versus non-homeostatic feeding and sort of the balance between those two processes. But through all of this, there's been an interest in carbohydrate, partly because it's the predominant source of calories in our diet, partly because it's very tasty, and partly because it does evoke a strong endocrine response when it's consumed, insulin, and so on. And so it's been a thread that's gone through these sort of phases in study of diet and obesity. So we were interested in carbohydrate and did what might be called an early systematic review / meta-analysis on dietary compensation to carbohydrates. And through that work, it became clear to us that much of the issue with compensation focused on the form of intake of carbohydrate. That is, it was largely, there was a large beverage component to carbohydrate intake. And when we looked at the studies and sort of focused on food form and its effects, it became very clear that it was carbohydrate in the form of beverage that was especially problematic. And we expanded that work, and it's our belief now that it holds for protein and fat as well. It's not the source of energy, it's the delivery system that may be particularly problematic there. And so that's kind of been our contribution in that realm. The other contribution, I guess, is that we were interested in the role of cognition in how people respond to foods. And so because when we make food choices, we don't open the refrigerator door and look at the array of foods in there and sample every one of them and then decide, oh, I'm going to have this one and this much of that one. And so we make those decisions cognitively. And so we were interested in that. And we designed a study that would try to capture that, where we had people come into the lab where we did demonstrations for them. And we told them that they were going to be consuming beverages or solid foods, and that they would either be a liquid in their stomach or they would be a solid in their stomach after they swallowed it. And we concocted a demonstration to sort of convey those concepts to them. And what we found was that just the thought that something would be a beverage in your mouth and be a liquid in your stomach was enough to change all of the post-ingestive processes that are activated when one eats or drinks. So people said that the actual mouthfeel differed. If they thought it was going to be a solid in their stomach, even though it was a liquid in their mouth, they said it was thicker. They said that if they thought it was going to be a solid in their stomach, they said they were more full after consuming it. They actually ate less over the course of the day when they drank it and thought it would be a solid in their stomach. It emptied from their stomach more slowly. It passed through their intestines more slowly. It evoked a different endocrine response, insulin, ghrelin. Just everything about it differed, just thinking that it was going to be one form in their stomach versus another. And I think that goes some way towards explaining why beverages are, in my opinion, problematic for weight gain. They just don't evoke the same magnitude of compensatory response as a solid food. And we are getting something on the order of 13% of our energy now from beverages. So it's a very substantial source and goes largely uncompensated. And so often we do science to prove the obvious. This is not anything unexpected. In clinical populations that experience early satiety, so maybe a cancer patient or the elderly, when we're trying to increase energy intake, what we recommend universally is to add a drinking event that yields energy, to drink a liquid meal replacement, for example. We don't recommend eating bars or another solid meal And I think the reason is we know it's much easier to consume those extra calories in beverage form than solid form. So I think it fits with intuition and common practice, but now we have some science to back it up.
Wonderful. Now, to switch gears a little bit, you studied how nuts can be part of a healthy diet. Please elaborate on those findings.
Yeah, this work started, I think, about 1996, when my department head, Connie Weaver, attended a meeting on nuts and health at the Presidio. And she came back and said, you know, this is crazy. People are saying that nuts may be included in the diet without promoting weight gain, and that there might be actual health benefits of including nuts in the diet. And I was interested in energy balance, and I found this intriguing because at the time, nuts were viewed as especially problematic for weight gain. They were high fat, energy dense foods, and were really discouraged. The consumption was really discouraged because they were viewed as high risk food for weight gain. And just at that time, there was a call for proposals from USAID. They had a program called a CRISP program, Cooperative Research Support Program. And in sub-Saharan Africa, they were trying to promote peanut farming and consumption. They viewed it as a very healthful food. It's relatively high in protein. And there had been, in the preceding years, a drought, and farmers had shifted away from legume farming to sugarcane farming, and that was not conducive to their health. And so they were trying to build back peanut agriculture. And so we thought, well, gee, you know, this is really interesting. In one realm, peanuts are viewed as the solution to hunger and poverty. And on the other hand, it might be viewed as the solution to improved compliance with weight management diets, even though they're high fat and high energy. So we were intrigued and decided that we would study. We started with peanuts, later moved on to almonds and walnuts, but to study how these nuts play in an energy balance. And so what I think we've contributed to the field is a mechanistic understanding of the role that nuts can play. And so, well, we've done quite a number of studies over the years, but perhaps the one that sort of encapsulated it was a metabolic study where we tried to measure all the sources of energy in and all the sources of energy out in individuals that were consuming nuts. And in that particular study was almonds. And what we found, which confirmed other work that was going on. By no means are we the only ones doing this, but there seemed to be three mechanisms that accounted for this observation that there was an inverse association between frequency of nut consumption and body weight in epidemiologic studies. One is they have very high satiety value, meaning that when one chooses to consume nuts elsewhere in the day, elsewhere in the diet, there is a spontaneous reduction of food intake, of energy intake, that offsets a high proportion of the energy contributed by the nuts. In our hands and in the literature, it's somewhere in the neighborhood of 70-75% of the energy from the nuts. Second, it turns out that the efficiency of absorption of energy from nuts is not as high as one might predict theoretically. That is, because of their high fiber content, and not just the fiber content, but the nature of the cell walls of the parenchyma of the nut. They're not easily digested, broken down enzymatically or microbially in our GI tracts. So they really have to be mechanically disrupted through chewing to liberate the energy contained in the cells. And people don't chew them especially well. And so somewhere on the order of, say, 7 to 15% or so of the energy from nuts is not bioaccessible, not absorbed, not accessible for our GI system to take it up and absorb it. So that accounted for another percent of the energy from the nuts. And the third, and this one is not as well established, but there are a few studies that show that chronic nut consumption is associated with an elevation of resting energy expenditure. Now, it's not high, maybe it's 5%, 10%, but because that component of energy expenditure is about 70-75% of daily energy expenditure, a small percent of that is actually substantial. So you put all three of those mechanisms together, and it largely accounts for the energy contributed by the nuts. And it kind of explains the epidemiologic studies, as I say, showing this inverse association, and the clinical trials that show that inclusion of nuts in the diet is not associated with weight gain. And the result of all of this is that the nut industry, and again, this is not just our lab doing this, but I think we made some contribution here. It turned the industry around. The nut industry was suffering from the view among clinicians and nutritionists that they were problematic for weight gain, to now a situation where they're viewed as healthful and a useful component in even diets that are energy restricted. So that was sort of the nut story, and it has branched now into effects on blood sugar levels and lipid levels and other dimensions. So the story is not done. It will go on in new directions.
Now, you've touched on this a little, but what is the effect of sweeteners on appetite, energy intake, glycemia, and body weight? You touched on body weight before.
Yeah. So again, dealing with the issue of public health and obesity, there was a good deal of concern about the role of low-calorie sweeteners in the diet, and even suggestions that they were problematic rather than helpful, that they would stimulate appetite, that exposure to them would stimulate appetite, the desire to eat something sweet, and lead to greater energy intake. We were intrigued by that and decided to study that. And our work, again, just part of a much broader literature, suggested that was not the case, that they didn't stimulate appetite. They did not stimulate the release of insulin, and there is a whole hypothesis about insulin driving obesity, but we didn't find that low-calorie sweeteners were problematic in that regard. So we think that sweeteners are not necessarily problematic for weight gain, and in fact are probably beneficial because they can play a role in maintaining the palatability of the diet without adding energy to it. And we have so few tools available to help people manage their body weight to not make available the option of using low-calorie sweeteners as a tool. I think is a disservice to a large segment of the population. Having said that, our most recent work has raised an interesting new question, and that is, we think of sweeteners as a common class of chemicals that have a similar property. They're sweet at concentrations that provide no energy or very, very little energy. But the reality is they are very different chemicals. And different chemicals would theoretically have different biological properties. So we designed a study to contrast several of the more common low-calorie sweeteners, so aspartame, Splenda, stevia, and Equal, and contrasted them with sugar intake and saccharin, as well. And what we found was really much to our surprise that saccharin, chronic consumption of saccharin, led to weight gain in our population that was very similar to the weight gain that we anticipated with sugar consumption. And this was delivered through beverages. But that Splenda actually was associated with a reduction in body weight. Equal and stevia actually were neutral. But the point is that over time, there was this spreading out of effects of the different low-calorie sweeteners on body weight. And it wasn't due to a shift in energy intake that we could measure. And it wasn't due to a shift in endocrine response that we could measure. But the changes in body weight were real. And so it has led to the question of whether we should, in fact, view all of the commercially available low-calorie sweeteners as a common class, or in fact, they are different chemicals with potentially different physiological effects and behavioral outcomes, health outcomes. And we are just at the beginning of the science on that. We may be proven wrong, but I think it's an area that's worthy of further study.
Interesting. Now, please define cephalic phase responses and discuss your work in this area.
Yeah, so cephalic phase responses are physiological responses to sensory stimulation. If you think about, so why do we have our sensory systems? They are there to provide information from our environment, both internal and external, that help us make decisions that enhance our likelihood of survival. Often it is advantageous to be able to garner that information in a time frame that allows us to react to it. So, for example, the sense of smell allows us to detect potential predators or toxic chemicals in the environment at a distance, and it gives us the opportunity to react to that in a way to protect ourselves. Taste is a more intimate sense, something that actually has to be in your mouth for you to taste it. But it is sort of that final bit of information that helps you make the decision to swallow or not swallow, which is a very fateful decision if, in fact, what you have in your mouth is toxic. They play an important role in food choice, in decisions to consume. But its role is actually greater than that, because our bodies also have to anticipate the nature of the physiological response that's required to handle this metabolic challenge, this meal that's about to enter the system. For example, if we're consuming carbohydrate and we over-secrete insulin, that will lead to hypoglycemia. It'll drive blood sugar levels down, and that's not desirable. If we have inadequate insulin response, we will become hyperglycemic. That's not desirable. So we have to know how to physiologically respond. And again, the earlier the warning, the earlier the information we garner that will predict the nature of this response, the better. And so these cephalic phase responses are directly related to things like gastric motility and gastric acid secretion, to endocrine responses in the GI tract, to exocrine responses from the pancreas, to changes in blood flow, to changes in renal filtering. Everything that happens physiologically upon consuming something is activated just by its sensory property. It may be the vision, it may be the odor, it may be the taste. And actually, there is a bit of a gradation there that the closer one is to actual ingestion, the larger are these cephalic phase responses. So swallowing is better than just tasting. Tasting is better than olfaction. Olfaction is better than vision, and so on. But all of them combined provide this early warning system that allows us to decide what to eat and then how to process it.
Interesting, very interesting.
And we've been interested in it. We've looked at it from the perspective of sweet taste and responses, bitter taste and responses, fat taste and responses, and think there is, again, much more science to be done there. What we're particularly interested in right now is the role of taste and smell dysfunction with COVID. So one of the hallmarks of infection is a loss of taste and smell. And if that's true, then one might predict that it will disrupt these cephalic phase responses. We've lost this early warning system. And if that's the case, what are the implications for, say, carbohydrate and fat metabolism? So it's our hope that we can start exploring that.
Mhm. So your research led to the groundbreaking finding that fatty acids are detected in the mouth, contributing another category of taste to the classically accepted ones of sweet, sour, salty, bitter, and umami. What led you to the research, and where does it stand?
Yeah, we started this work back when I was at Monell. We were interested in why people like to eat so much fat. And as we were studying it, we realized we really had to study the mechanisms of how fat is detected in the oral cavity. And the prevailing view at the time was that we couldn't possibly taste fat because there was no molecule, no chemical in food that would be appropriate to bind to a receptor, which we didn't have any idea would exist. And so there was no mechanism that could account for that. And that was the view of the nutrition community. But the food science community had known for a very long time that free fatty acids are very unpleasant from a sensory perspective. And they go to great lengths to keep concentrations of free fatty acids below detection levels in foods. And so when we started studying the mechanisms of fat detection, we realized that these two worlds were not speaking with each other, and that the science was evolving, showing that free fatty acids were in fact signaling molecules elsewhere in the body. And so we thought, well, perhaps also signaling in the oral cavity. And so at that time, Tim Gilbertson had started work identifying receptors for free fatty acids in the oral cavity. This was rodent work. And other work progressed showing that there was that there were receptors on taste receptor cells that could bind with fatty acids. And drawing on the food science literature, we realized that there are, in fact, free fatty acids present in food inherently, and that when we chew foods, they are liberated, and that concentrations may be adequate for detection. But clearly, there were food sources that would be high in free fatty acids, oxidized fats, frying oils, for example, that were used, or old oils exposed to light, and so on. So there are clearly possibilities for free fatty acids in the oral cavity. New literature suggesting there were receptors for them, evidence that fatty acids are signaling molecules. And so it led to our work trying to put all of that together. And one of the ways we did psychophysical experiments, sensory experiments, but I think the most compelling evidence is the cephalic phase work that we were just talking about. So we put oral fat stimuli or foods that mimicked fat but had no fatty acids in them in people's mouths and measured triglyceride responses, the rise in triglyceride after this oral exposure, and demonstrated that in fact, just oral stimulation with a true fat source led to a rise in triglycerides. We attempted to mask the textural properties, the olfactory properties. People wore nose clips. We added thickeners to the stimuli to mask the tactile sensations and so on. So to the best of our ability, we narrowed it down to taste. And so the fact that we would get a physiological response to just sensory stimulation is basically evidence that in fact there is a chemosensory detection system for fatty acids in the oral cavity. Other groups have now replicated that, and I'm delighted that that's the case. Now, whether it's in fact another basic or primary taste quality is going to take time to be established. We've suggested that there are a set of criteria that might be used to answer that question. We think, for example, there should be evidence that there is some adaptive advantage to having that system. All other systems, at least teleologically, play a role. Sensitivity to bitter to avoid toxins, and sensitivity to carbohydrate to be able to localize that in the environment and want to consume it. The story with fat is a little more complex because these fatty acids, as I just told you, are extremely unpleasant. They would discourage consumption, but we have essential fatty acids. We need to consume fat, and it is the most energy dense source of foodstuffs in the environment. So we have a lot of reason for wanting to consume it, but from a sensory perspective, we wouldn't want to consume it. So the story is not straightforward. It may be that, in fact, the taste component is a warning signal, just like bitterness is for toxins. The taste component says, don't consume this source of fat because it's rancid, it's not helpful. But the tactile component of fat perception, actually the triglyceride part of dietary fat, is pleasant. It's appetitive. And so it might be that balance between taste and texture that is really helping us make that decision. So it's more complicated. It's not settled yet, but that's one of the criteria and where we stand on it. Another is you need an identified class of effective stimuli. And I think fatty acids are representative of that. So that one is well established. You need a unique transduction mechanism that is converting the chemical signal, fatty acid, to an electrical signal that goes to the brain. Animal studies are now, I think, filling that criteria. We need evidence that neural signal is decoded in gustatory cortex in taste centers and evokes this percept that we call taste. And again, there are animal studies that are now, I think, filling that one. It has to be perceptible and unique. This has been one of the hardest ones to document because there is no vocabulary for fat taste. There is no word, and so it's hard to study. But Cordelia Running, a graduate student in our group, took this on, and we designed an experiment that didn't require the use of a lexicon. Instead, people just had to say what move samples that were similar in sensation into groups and ones that were dissimilar into other groups. And using statistical methodologies, one can draw inferences from that. And indeed, that work demonstrated that free fatty acids were detectable and were unique. They didn't overlap with sweet, sour, salty, bitter, and umami, the other presumed primaries. There are people that still disagree with us on that, but we think that we made a contribution there, and that it has to evoke. And our final criteria is that this when activated, this taste system has to evoke a physiological response, and that's what the triglyceride response that we've talked about fills. So I think we've come quite a ways in meeting all of the criteria. We have proposed a name for this sensation. We call it oleo gustus. The Latin oleo for fat, gustus for taste. Again, we'll see if the scientific community decides to adopt it or not. But that's where we stand, and it's a fascinating area because the prevailing view is that taste is comprised of a very limited number of primary qualities, and sweet, sour, salty, and bitter have been considered fundamental for a very long time. Umami has been added more recently, but many people believe it now. Adding fatty now starts to raise the question of just how many primaries are there. And other science is suggesting that there may be multiple, that calcium may be a taste, and carbohydrate, short chain saccharides may in fact have a taste, and water may have a taste. So it's challenging conventional wisdom about just what constitutes this fundamental sensory system that we have. So it's a very exciting area.
Thank you. It's very interesting. So to switch gears a little bit, what have you learned that was unexpected while collaborating with others?
Well, I have to say the fat taste story is the biggest. The idea that taste is comprised of a limited number of primaries is so ingrained in sensory science, and the fact that it has credible evidence now to challenge that view and open our understanding and really lead to the recognition that the mouth is unique. It's a special place, but it really is part of a continuum through our entire GI tract, and our GI tract communicates so effectively with peripheral systems that this idea of a continuum that really starts with taste is exciting, novel, and I think ripe for a lot of new settings.
And now please share a program or project that taught you something you did not expect.
Well, I guess I would go back to the nut story on that one. Again, in the early 90s, nuts were viewed as problematic, and now they are viewed as healthful. They are the poster child of a scientific effort that had the nerve to take on the naysayers by supporting good science, and again, many people in this area, and turned around the perception of this food source. It's really quite dramatic in its implications for the food industry. We seem to like to vilify foods, different ones at different times. But I think the lesson we learned through the nut story is that we have to make decisions based on science, not intuition. And this story that evolved provides a rationale for challenging other concerns in the diet.
Mm-hmm. Well, we're coming to the end of our interview. Is there anything else you want to discuss?
Not so much, but if I can leave a parting thought, my whole career has been work at the interface of different fields of sensory science and nutrition science, food science and sensory, even psychological sciences and nutrition science. And so it's forced me to interact with scientists taking many different approaches and using different methodologies. And what I've come to learn is that all of them have a place and contribute to the totality of the evidence base. And my fear is that in nutrition, it's true in many sciences, but in nutrition science in particular, I think there's a polarization underway that is destructive to the field. It not only is harmful in terms of collaborations and advancing the science, but it's harmful in translating that science into the public health arena, into the clinical practice. And so it's so important to respect each other's work and the different branches of science that may contribute pieces of the puzzle. And I hope we can take a more positive and encompassing attitude towards that.
Wonderful. Well, Dr. Mattis, thank you so much for your time and your body of work, and congratulations on your award.
Thank you so much. It's been a pleasure to talk with you.
Thank you.
The USDA is an equal opportunity provider, employer, and lender.